Hello, I'm Mr. Muskeluk, your AP Chemistry teacher at ChemAdvantage.
Well, we have a nice stoichiometry problem here with a little bit of history in it, and it deals with this mercury oxide, this mercuric oxide, mercury 2 charge. Interesting compound, a beautiful, beautiful orange, but it's not one that you really want to mess with. Here's the description of it. You can see their powder here, and they've got its atomic arrangement. Mercuric, the old name. It's a compound that has both mercury and oxygen in it. One of the things I want to bring up, though, is the health problem here, and that's this. It's a very toxic substance. They give you its formula weight. We'll deal with that later. But it melts at 500 degrees, and then it decomposes. Toxic for inhalation, cumulative effects, neurological hazard, highly toxic. So this is not an experiment you want to do. So this would be something that you will want to watch a video of, but not try yourself. I'll end up showing this done in an experiment. I've got a video that I'll use as a thumbnail so you can watch how it's done. It's done underneath the hood. It's done by the North Carolina School of Science and Mathematics, and I'm sure they did it underneath careful safety conditions. So watch the video as we talk about this, because if you heat mercury oxide, you end up getting pure mercury. This is this mercury, whose vapors you want to stay away from, which makes this an dangerous experiment, in addition to the mercury oxide and our wonderful oxygen that we end up needing. Nice experiment to make oxygen, but one you want somebody else to do. Well, the first thing we've got to do is balance this reaction. And balancing it means that we will look at the atoms. Here we've got an atom of mercury. Now, this experiment was done in 1774, and Priestley thought that the gas produced was referred to as dephlogistonated air. Later, Lavoisier figured out that it was oxygen, and then about 50 years later, we've got our Dalton, who came up with the ideas of atoms that allow us to balance this reaction. So this was an important era in chemistry. Well, if we have one mercury to start off with, we know atoms are conserved. We have one atom of mercury as a product, so it looks like it's balanced. But the problem is here we've got O2, one of our diatomic substances that you should remember: hydrogen, nitrogen, oxygen, and all of the halogens, when you have any amount of them, will become diatomic. The atoms, separate atoms, come together. So this isn't balanced. One oxygen can't make two. So the only thing we can do, we can't change the formula. This is the formula. It is one mercury to one oxide. So we can't change the formula. We can change the amounts. This coefficient of 2 says now we've got two Hg's and O's. You're forced to make both of them 2. And that gives us an oxygen. And of course, that means we're going to have to go back here and say we have two oxygens here. Now, you can view this in terms of atoms, two HgOs, making two Hg's and an O2, but you can also view this in terms of moles, because moles are particles too. And that's how we're going to look at these. 2 moles of mercury oxide and 2 moles of mercury. Now, sometimes this is balanced using a 1, 1, and a half in thermochemistry, but we prefer not to use fractions. We prefer to use whole numbers in most cases. And this is one of those most cases. So as you saw in the thumbnail, you heat this, you get some bubbles of oxygen gas, which can be collected pretty easily and measured, 2.80 liters. Now, this must have been done in a cold lab, because this is at standard temperature and pressure. 1 atmosphere and 0 degrees Celsius. Unusual for 0 degrees, but that's the way it is. Now, here's the question. What were the masses of each substance in the reaction? Well, we only have the volume of gas. They didn't measure the mercury oxide. They didn't measure the mercury. So let's figure out what's happening. This is the conversion factor that you should remember. We'll deal more with this when we deal with gases. This is a relationship between a volume of any gas at standard temperature and pressure, even has its own initials, STP. If you have 22.4 liters of gas, any gas, this could be nitrogen, this could be helium, this could be sulfur hexafluoride. If it's a gas at this temperature and pressure, you have 1 mole of it. That's our conversion factor. It's on the AP equation sheet. If you see a gas problem where there is 0 degrees Celsius and 1 atmosphere of pressure, think 22.4 as a conversion factor to find moles. And you know, in AP chemistry problems, you're going to have to find moles. First thing we have to find out, the amount moles of oxygen in this should be 2.80. Oh, error, make this 2.80, ignore that 2.79. At standard temperature and pressure of oxygen. Well, as soon as we have standard temperature and pressure, we know we can use this conversion factor. 2.80 liters of oxygen. Conversion factor. We want to get moles, so we put the 1 on top, the 1 mole of gas, and the 22.4 liters of gas at the bottom, and the liters cancel out. Calculator time. Pull out my TI, 2.8. We're going to divide by 22.4, that magic 0.4. Double check those numbers and enter. Nice, 0.125, 1/8. And that's our answer. 0.125 moles of oxygen that are produced. Now, once you've got the moles of one substance in a balanced reaction, you're going to be able to find all the rest. They're going to be a piece of cake because these coefficients tell you about moles. So this is beautiful. This is the breakthrough that you want, and that's why this 22.4 liters is important. And now we can go on to the next part of the problem. Using the balanced reaction. We talked about that before. 2, 2, 1. Predict the amount. For chemists, amounts are typically moles of mercury. Here's our mercury produced in this reaction. 2 to 1. Calculator. I'm going to save this 0.125 because I think I need it later. So I'm going to store it as X. I see 1 to 2 times 2. Easy enough. 0.25. You could have done that in your head, but that's the moles of mercury produced in this reaction. 0.25, and you're going to make that 0.250. Even though the calculator says 0.25, you know there's the 3 significant digits, so you're justified in saying this thousandth of a mole. You know this thousandth of a mole times 2, you know this thousandth of a mole. So we now have our moles of mercury. Let's keep on going because we've got a balanced reaction. We've got a couple of moles. Let's find the mass of oxygen produced in the decomposition and the mass of mercury. I'll pull my calculator up and say, wait a second. I've got the moles of mercury. Why don't I just multiply by the molar mass to get the mass and make this answer next? I'll look up mercury. I've got the periodic table right here. Mercury, 200.59. So I know my moles of mercury. Moles times atomic weight will give me grams. 0.25 times 200.59. Enter. 50.1475. That's more than I can possibly need. I'll round that off to 3 significant digits. Write that out very nicely as 50.1 grams. My calculator gives me more sig figs than I need, so I'll just write this down to show that I know about numbers and rounding. Well, we have our oxygen, which we have to find next. The oxygen mass amount in grams produced by this reaction. And I remember that's my X. So I can just go X. And this is where a common mistake is made. People say oxygen. They look up oxygen on the periodic table and they see 16. Go to the formula. It's diatomic. Remember your diatomic gases. Don't embarrass your teacher on a test by using 16 for oxygen. Oh, that's so sad. Let's enter this and multiply, and we get 4. And speaking of showing your teacher that you know about sig figs, you're not going to write 4. You're going to write 4.00 grams. 4 is only 1 sig fig. That if you just say 4, you can say, oh, it's anywhere between 3.5 and 4.5. But no, we know this to 100th of a gram. Next, notice I put down no calculator because I don't want you to use the calculator for the last part of this answer. The mass of mercury 2 oxide that reacted. Now, we could say, okay, I've got, using our coefficients, 2 HGO. I know I have 0.25 moles of HGO. I'll take that 0.25 times the molar mass of mercury plus oxygen. No need to. This reaction, the mercury oxide, one substance, makes these. Indeed, we have 1 making 3. But in terms of mass, we know the mass is there. This has a certain mass. There's a conservation of mass. So whatever the mass of mercury and oxygen is, must have been the mass that we start off with. And that's going to be easy to calculate. This is why you don't need the calculator. 4 grams of oxygen. 50.1 grams of our other product. So we must have started off with 50.41 grams of mercury to oxide. And we've got this stoichiometry problem taken care of. It's ours. We know the atoms. We know, in this case, a volume of gas. We know the moles. We know the grams. So if you, and don't do it, heat up some mercury to oxide, you can predict what is going to happen. Stoichiometry is beautiful. I love chemistry.